Alright, so welcome back for part 2 of Introduction to Physics. And just a little reminder is that you should be following along with the website. So the previous lecture's homework was to print this out and put it in your notes. Hopefully you've done that, and hopefully you read it before you printed it. If you haven't, you need to read this, because it's going to help you a lot. And it'll also help you figure out what you don't understand and what you need to ask questions on. So today we're going to talk a little bit about things that have to do with making measurements in the lab. And the first thing is the difference between accuracy and precision. And that word's really hard to say sometimes. So in everyday language, we kind of use these two terms interchangeably to mean the same thing. But in science, they're actually different things. Precision is our ability to obtain consistent results over and over again. And that means your data points, no matter how close they are to the real value, your data points are all close to each other. So when you perform a measurement, you may get a really crappy value. It's nowhere near what it should be. But if you get that same crappy value over and over and over again every time you run the experiment, your results are precise. On the other hand, accuracy is a measure of how close your value is to the actual value. So, how close were you? As an example, I am 5 feet and 5 inches tall. If I take a measuring tape and measure myself, and I measure myself to be 4 feet and 4 feet and 11 inches, or 5 feet and a half inches, or just 5 feet 0 inches, are these accurate results? No, because I'm about 5 or 6 inches off. However, are they precise? They're fairly precise. They're all within an inch, inch and a half of each other. So if we look at these targets and the data points on the targets, we can figure out if they are accurate, precise, or both. So for the first one, we have 3 little data points, and they're all around the bullseye. So that's good. That means they're accurate. But they're not really clumped together. They're kind of spread all the way around the bullseye. So this target is only accurate. It is not precise. For the second one, our data points are all clumped together, which means they're precise, but they're nowhere near where they should be. So they are not accurate. They are just precise. And the last target, the data points are all clumped together and they're exactly where they should be. So this third target is accurate and precise. And that's what we're aiming for. We want our results in the labs to be not only accurate, but also precise. We want to be able to get the same results over and over again. So which is this? Alright, well, how many arrows are there? There's 1 arrow. So do we have any other arrows to compare to? No. So if you only have 1 data point, or in this case 1 arrow, it cannot be precise because you have nothing else to compare it to. So this is not precise. Is it accurate? Well, where was he aiming? Hopefully the archer was aiming at the apple and not at this guy's shoulder. So he was not very accurate. So it turns out this picture is neither. When we make measurements, we are human beings, and our measurements are only as good as the tools that we're using. So no measurement is ever going to be exact. There's always some uncertainty, and that's due to limited instrument accuracy, right? So, for example, we have this block of wood, and we can measure how long it is. And remember, these are centimeters and not inches, because we measure in metric. So this block of wood is 8 centimeters, 8.5, 8 and 1, 2, 3. It's about 8.8 centimeters. Can we measure between the millimeter lines, or the really small tick marks? Not really. I mean, between photo resolution and how well our eyes can see and how well the ruler can measure, we really can't measure past a millimeter. or be 0.8 centimeters. So that means we have an uncertainty because we cannot measure past that amount. And it could go either way. This could be 8.7 centimeters. It could be 8.9 centimeters. So what we do is we write this uncertainty one of two ways. We can write it as an estimated uncertainty with a plus or minus sign, which means give or take. Or we can write it as a percent uncertainty, or a percentage of how much our uncertainty is. So estimated uncertainty is when you take your measurement, in this case it was 8.8 centimeters, and we say give or take a certain amount. So in this case, it's give or take a millimeter, or 0.1 centimeters. So we write it as 8.8 plus or minus 0.1 centimeters. And that means it could be 8.7 or 8.9 or 8.8. It could be between any of those. Percent uncertainty is when you take your uncertainty, in this case, the 1 millimeter that you would give or take, you divide by the value you measured, or 8.8 centimeters, and you multiply it by 100. And it turns out your percent uncertainty is about 1%. So you're about 1% off in either direction, potentially. You'll get some practice with this on the homework, so if this is confusing, definitely ask questions. So our ability to measure things and be accurate can be seen in the number of significant figures of a number. And the number of significant figures is the number of reliably known digits in a number. So if you can measure to the nearest millimeter, like on the block of wood, you're not going to write your number as 0.000008 because we cannot reliably measure to that number. We don't know that number reliably. So you can usually figure out how many significant figures are in a number by just looking at it. For example, 23.21 has 4 numbers in it, and they are all non-zero numbers. 2, 3, 2, 1. Any non-zero number, no matter where it is, counts as a significant figure. So this has 4 significant figures. 0.062 has 2 non-zero significant figures, so those automatically count. Now the zeros are the tricky part. In this case, the zeros do not count because they come in front and they act as a placeholder. So these zeros do not count. So 0.062 has 2 significant figures. Finally, 80 could have 1 or 2 significant figures. And that's because 80 might mean we can only reliably measure to the nearest tens of a kilometer. So it could actually be 85, but we can only measure to the nearest tens of a kilometer, so we have to estimate to 80. Or it could mean that we can measure to the ones place, and it is exactly 80 kilometers. In that case, it would have 2 significant figures. However, if it had 3 significant figures, you would need to write it 80.0. Because the zeros come after, they tell you, I can reliably measure to this place. So we need to count it as a significant figure. I measured, and it's not 80.1 kilometers, it's exactly 80.0. That's what this means. So calculators are not your friend when it comes to significant figures. They just kind of spit out a whole bunch of numbers. Most of the time they'll give you way too many, but sometimes they give you too few. And you need to know how many significant figures is appropriate given the numbers you're dealing with. So, as an example, the top calculator shows the result of 2.0 divided by 3.0. What is the appropriate answer? Well, if you look at this number, it's huge. you can tell just by looking at it and by looking at the numbers you started with that it has way too many significant figures. But how do you know which number to round to? Well, you count the number of significant figures in the numbers you started with. So 2.0 has 2 significant figures. The 0 at the end counts because it is telling us that we measured precisely to the 10th place, and it is a 0. And the same with 3.0. Both of these have 2 significant figures. So that means we need to round this number to 2 significant figures, which would be 0. Does that count? No, because it's in front and it's a placeholder. So 1 significant figure, 2 significant figures. And I rounded up to 7 because it's 0.666. Okay, well, what about the bottom calculator? The bottom calculator shows the result of 2.5 times 3.2, and the answer is 8. Is this an appropriate number of significant figures? No. It may look fine because it's a nice small number, but 2.5 has 2 significant figures, and so does 3.2, so your answer should also have 2 significant figures. The answer 8 only has 1. But it didn't give you any other decimals after. So that means it's exactly 0. And we put that 0 at the end to show that we measured accurately to 2 significant figures, and the last number is 0. Okay, so now on to scientific notation. You should all have some experience with scientific notation in chemistry because there's a very special number that you have to deal with in chemistry quite a bit, and it's gigantic. So scientific notation is a method of writing very big or very small numbers easily. So this number, 6020000 on forever, is obnoxious to write out. You would not want to write that out every single time you had to write it. So we use something called scientific notation. Scientific notation is when we abbreviate a number or make it smaller by using a multiplier with an exponent. So times 10 raised to a certain number. Well, how do you know what that certain number is? What you need to do is move the decimal point. Sometimes you are going to physically move it because it'll be easier, but most of the time you'll be able to move it in your head. In this case, we're going to move it manually to see what's going on. So if we have this giant number, the decimal place is way over here at the end. And what we want to do is move our decimal place up this way to make our number shorter. So we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. We moved it 23 places over. So now our decimal point is right here, and we can write it as 6.02. We don't want to get rid of that 2. We want to keep it there because it was important. And we don't want to write 602 with the decimal point at the end. It's just not convention. So we have 6.02 times 10, and how many places did we move it over? We moved it over 23 places. Now, this is a really big number. But what happens if you have a really small number? If you are moving the decimal place in the other direction, so if you had a really tiny number and you were moving your decimal place to the right, your exponent would have to be negative. So let's try a couple together. And this is a great website down here for some practice. So if you have a hard time with this, you should go to this website. You can see the link up here. And you should practice scientific notation. So let's go ahead and try a few. Maybe. Yeah. Okay. So the first number we're given is negative 0.00857. Well, first of all, is it a really small or a really large number? It's a pretty small number, so we're going to move our decimal place to the right. 1, 2, 3. So we have 8.57. But we're missing something. We can't forget the negative in front. And the negative in front does not mean automatically there is a negative exponent. The negative in front literally means your number is negative. So it goes in front of your base number. And now for the exponent. How many places did we move it? We moved it over 1, 2, 3 to get it to the new spot. But did we move it to the right or the left? Well, we moved it to the right, which means that this is a really small number. So our exponent is going to be negative. Ta-da! Hey, nice job. All right. So let's see if we can try another one. All right, so this is reverse scientific notation. We're given negative 7.43 times 10 to the negative 1, and it wants us to write it out. Well, we know that all the numbers are going to stay the same, and that there is going to be a negative in front of our number because it's negative 7.43. So we put in the negative, and then 743. But where does our decimal place go? Well, our exponent is negative, which means that our answer is going to be smaller than this one. We move our decimal place to the left. And how many places do we move it? We move it over 1 place. So if we move it over 1 place to the left, our decimal point will be in front of the 7. 0.743. Let's see if this is right. Ta-da! So definitely go to this website, practice, and really understand scientific notation and what it is. You will also have to do some of that for your homework tomorrow night and on your problem set. So your homework for tonight is to do this one problem, but you should have 5 answers. So you need to label each of the following targets as precise, accurate, both, or neither. And all of the data points are green X's on the targets. So go ahead, look at this picture, write down your answers, and be ready to hand them in.